So I'll begin. My name is Katarina Klos. I am a second year PhD student at the University of St. Andrews, and I am working with Ian Burnell and James Worcester using Phantom to look at how magnetic fields can influence the formation of massive stars. So what is the motivation? Why do we care about massive stars? Well, despite making up only a small percentage of stars in the universe, they have a significant impact on their surroundings and on star formation in general. This is through feedback processes which occur over the entire course of their lifetimes, from their formation up until the end as supernova. And they have an impact of star formation in their vicinity, and understanding their formation is vital if we are going to understand star formation as a whole. So what's the problem? So for the past 30 years or so, it's been known that high mass star formation probably proceeds in a different way to their low mass counterparts. This was first identified by York and Krugel with the radiation pressure problem, which suggested that for protostars greater than about 8 solar masses, radiation pressure would limit their ability to grow much beyond 10 solar masses. High mass stars also require high accretion rates in order to form within the typical star formation timescales. And in general, though subsequent studies have begun to remedy some of these questions, other differences for high mass stars still remain, such as the fact that they're almost entirely found in clusters, whereas their low mass counterparts can be often found in relative isolation. And also that these clusters tend to be mass segregated very early on, which is something that we also don't necessarily see for smaller mass clusters. And so some of these questions have led to the development of two theories for high mass star formation. One is known as the turbulent core model by McKee and Tan, and the other one is competitive accretion by Burnell et al. 2001. So I'll briefly explain what these are. So for the turbulent core model proposed by McKee and Tan, we extend the Shu, Adams, and Lozano description of low mass star formation up to higher masses. They define two terms which are very important. So we have clusters which form from clumps and stars which form from cores. A clump is typically about 1,000 solar masses and loosely bound, whereas cores are more tightly bound and about 10 to 100 solar masses. And instead of fragmenting as these cores collapse as usual, they're supported against their fragmentation by supersonic turbulence, which is a component of star forming regions. And so they initially, in this initial proposition, they suggested that for a given density, you may be able to form higher mass cores without fragmentation due to this turbulence. In contrast, so this gets around the issue of having to accrete mass onto a low mass protostar. And this model also predicts that the cores and clumps which are forming stars are quite smooth, and the star formation is quite a slow process. Smooth and round, yeah. So in contrast, we have competitive accretion. In this model, you have small n clusters which form from the collapse of gas clumps. Initially, the protostars in these clumps are all approximately the same mass at about 0.01 solar masses. And you have protostars at the center of these clumps sitting in a deeper potential well. So they're able to accrete mass from their surroundings more effectively than stars on the outskirts of these clusters. And this is what will allow them to attain their higher masses on shorter timescales and potentially overcome the radiation pressure issues as the mass flow rate is so high. So with this in mind, this leads on to the work I'm currently doing. So it's based on a study by Dobbs, Burnell, and Clark from 2005, which was an analysis of the original McKee and Tan model. In the Dobbs work, they started with a 30 solar mass core, which had already formed and was supported by an initially turbulent field. And they found that the effects of this turbulence was not enough to prevent the core from collapsing and fragmenting further to form lower mass protostars. However, in this study, they did not include magnetic effects. And so, as James just highlighted, magnetic fields are quite important in star formation if we want to do it properly. So this is kind of the motivation for my work. So I'll just describe some terms as well. So you have the mass flux ratio, which is just the mass of a given region divided by the flux through that region. And we can also quantify this in terms of the critical mass to flux ratio. So this critical value is the point at which gravity begins to dominate over magnetic support in a region. So if we divide the mass to flux ratio by this critical value, we see that you have a supercritical region when this mass to flux ratio in units of the critical value is greater than 1, and subcritical regions are less than 1, and supercritical regions will collapse due to gravity, and subcritical regions will be supported by magnetic effects. And so when you actually look at star-forming regions, we see that globally, giant molecular clouds are subcritical, which indicates that they are supported by their magnetic fields, but cores are supercritical. And in general, star-forming regions are supercritical, having a mass to flux ratio of a few times the critical value. But just because they're supercritical doesn't mean that magnetic fields aren't potentially slowing down or having an effect on the star formation ongoing in these regions. So we can see a comparison here between a region which wouldn't have a magnetic field versus one that would. So if you just go based on thermal Jeans mass arguments for a 100 solar mass cloud of radius 0.25 parsecs, if you just work out the thermal Jeans mass in this region, you could expect a Jeans mass of about 5 solar masses. So if there was a significant thermal support going on, you would expect cores of about 5 solar masses. But if you then look at predictions for the magnetic Jeans mass, which is the mass of a region supported by a magnetic field, then you see that there is, even if you are supercritical, you could expect a significant degree of enhancement to the objects that you could expect to be supported in these regions. And so in the most magnetized case, so you could expect a 40 solar mass kind of magnetic Jeans mass in the most idealized case. And so all I've done is just rearrange the mass flux ratio in terms of the critical value to determine these magnetic Jeans masses. And so with this in mind, the method I'm using to study these effects is obviously phantom. That's why we're here, and I'm making use of the fact that you can simulate both ideal and non-ideal MHD. I'm currently using ideal MHD, even though James just impressed how important non-ideal is. And so the initial conditions I use are, right now I'm looking at a 100 solar mass sphere with a radius of 0.25 parsecs in a box with periodic boundaries for the magnetic fields. The sphere is a uniform density of about 10 to the minus 19 grams per cubic centimeter, and it's loosely bound with a turbulent Mach number of 6.59. And I look at a range of mass to flux ratios from the most strongly magnetized case of 3 down to 100 for the magnetized runs, and a mass to flux ratio of infinity basically means that there is no field in the cloud because the mass to flux ratio is proportional to 1 over b. And the B field is aligned with the rotation axis. So here I have videos of the 6 simulations I ran. They go for 1 free fall time, which corresponds to about 0.2 million years. In this corner, we have no magnetization, strongly bound. Also no magnetization here, more loosely bound, and then the full magnetized cases. And as we can see over the course of one freefall time, as you increase the amount of magnetization, the amount of structure which appears to form in the simulations is smoothed out. And you get much more filamentary structures forming as you decrease the amount of magnetic support, which is probably unsurprising. We can also see this when we look at the density evolutions in X, Y, and Z for each of the simulations. And so we see that the strongly bound cloud attains very, very high densities in this time. And we see a lot more pronounced structures forming as you, like density spikes, as you decrease the amount of magnetization, which is in line with what we saw in the previous slide. But all of this is done quite by eye. So we want to actually quantify what we're observing. So what I'm doing is I'm identifying cores by using a core or clump finding algorithm for the simulations once they're done. And so the first thing I want to do is to set a kind of dense particle threshold for what separates a region of the cloud as a core, as opposed to just the rest of the cloud. So I set the threshold based on this value of eta, which comes from Schneider et al. 2015. Essentially, it's the point at which the distribution of particles goes from log normal to more of a power law description. So particles in this region are, this break kind of signifies the point at which material becomes self-gravitating. So beyond this density threshold, material is under the effects of gravity. So I use that as a kind of break point to identify what is part of a core and what isn't. And then I take the log mean of this value to identify the lead particles of these cores. And the final constraint to be identified as part of a core is that the material is gravitationally bound in that core. So that is in line with the description by McKee and Tan.
3 minutes.
Once I do this analysis, we see quite a spread in the range of masses identified. So this is the increase in magnetization along the x-axis. So the most magnetized case is this one, and that corresponds to, as I showed before, a mass flux ratio of 3. And so at 1.5 freefall time, I've chosen this value because at 1 freefall time, the algorithm actually didn't identify any cores. So what we see is that whilst there's a spread of masses that we can see of cores which contain both gas and potentially sinks, the one main thing that we can take away from this first analysis is that like the maximum mass of the core does appear to increase with the degree of magnetization, but it's not necessarily something which could be called a massive core. Like in the most magnetized case, I only have the most massive core, which contains also gas and is not just a sink, is only about 1 solar mass. And so it'll be interesting and important to continue this analysis to later times, and also to higher masses of the initial collapsing cloud. Similarly, when I look at the densities, the majority, sorry, not the majority, a few of the identified cores have passed the threshold for becoming a sink, but they obviously haven't passed other checks to become a sink in that region. But a number of the cores are approaching the threshold value for becoming a sink. So it suggests this is a good indicator of what could be identified as a core. And finally, when I look at core morphologies, I see a range of shapes. I do want to quantify this more robustly. And so you can use the slope of density power law, again, from Schneider et al. To kind of quantify whether things are more spherical or elongated. But obviously this description is an important one as opposed to just looking by eye, because if we look at the different orientations for looking at these cores, based on the orientation that you're looking at them at, they can appear quite different, especially if they're quite irregular. And so in conclusion, I'm simulating the collapse of high mass clumps to analyze the properties of cores which will form. And I want to look at the masses, lifetimes, and morphologies of these cores that I identify in the context of McKee and Tan 2003 to reevaluate the turbulent core model and see if it can be remedied with the effects of magnetic fields included. It does appear that magnetic support can increase the core masses that are forming, but not necessarily up to what is required for massive star formation. But I do have simulations looking at higher initial cloud masses and size scales for clumps underway. And I want to study the evolution of the cores which forms in these simulations as well. That's it. Thank you for listening.
Thank you, Katarina, for the great talk. Do we have any questions? Daniel?
Nice talk. I was just wondering, so you said this magnetic genes mass would suggest that you get like a minimum star mass of like 37 solar masses or something in the most magnetized case. So, I mean, I assume you could prove that wrong if you form any star that's going to be less than 37 solar masses.
Yeah.
Does that seem likely? I mean, it looks like you're just about to run your simulations a little bit longer, but it looks like you're already close to forming low mass objects. Is that fair?
I'm sorry, I'm not entirely sure what you meant.
So it looks like if you run your clusters a bit longer, you are going to form low mass objects.
Yeah.
Which presumably means that genes mass of the magnetic genes mass isn't something that tells you what the mass of your stars is going to be. Is that true?
Yeah. Yeah, I would agree. I think that more than anything, this is kind of more like I wouldn't necessarily expect these exact numbers is the point, but it's more to illustrate that you should expect some degree of enhancement, if that makes sense. Like I put them in more illustratively than what I would necessarily expect to see. And again, like in these simulations, obviously, they're using ideal MHD. So the amount of magnetic support in the simulations as well is probably a lot higher than you would necessarily expect, like the coupling in real star forming regions, if that makes sense.
Hi, thank you. It was a great talk. I just was wondering when you used your clone finding algorithm, would it be possible that some of your clumps in the future disperse, like they were like transient structures, and what it will be modify some of your results if you are considering like very dense clumps in the present time, but then in the future they disperse?
Yeah, so that is something as well that I am working on looking at. It's something which I didn't mention in this talk because I'm trying to work out how best to approach it. Because obviously, as I said, like you identify a core based on the Lie particle, but you also need to look at, so it is possible that Lie particle or whatever could move out of a dense region further on in the simulation, but it's also something that I was considering is how material moves between cores and like how you identify one core from the next and whether it's the same object and how much interaction it's having with its surroundings as well. So that is definitely something that I am thinking about and I'm aware of. And I've only analyzed at one point properly at this point, and so it will be really interesting to see how analysis with time will affect the results too. Thanks.
Yeah, thank you.
Any more questions? No. Actually, I had a quick question, which might be a bit naive. I was curious about, you're talking about massive star formation, and we know that most massive stars form in binaries or higher. Is this something you see in your simulations?
Well, so my simulations right now really don't go past the, when I say core, I'm not even like, that does not even represent a star. It's still much too big. So the resolution for that kind of for commenting on that is it's too low on these simulations. I need to go to smaller size scales, I think, and evolve for longer to really be able to say anything on that.
Okay, great, thanks. All right, well, if there's no further questions, let's thank Katarina again.
Thank you.